In the 1950s, mechanical engineering was at the heart of industrial progress. From designing engines and machines to improving factories and transportation, engineers shaped the technology that defined a new era. It was a time of slide rules, drafting tables, and hands-on problem-solving long before computers transformed the profession. This rare footage takes us back to the workshops and offices where ideas became machines, and machines powered a growing world. Welcome to Industrial Heritage.
This motion picture has been made to help you men who have chosen mechanical engineering as your profession. Perhaps you've considered the idea of working for a chemical company. Perhaps, like some mechanical engineers, you have wondered what a chemical company wants with men of your training. Perhaps you wondered whether you'd be working for chemical engineers. Or maybe you can't see how a mechanical engineer would get very far in a chemical company. That's why we want to show you something of what goes on at DuPont, where your advancement depends more on your interests and ability than on your field of training. Keep in mind throughout this visit to DuPont that the chemical industry is a growing one, growing by leaps and bounds. Just to give you an idea, at DuPont, in the first 5 years after World War II, over $700 million were invested in the manufacturing side of the business. There are now more than 70 plants in 25 states. No one actually can tell where the end is, but we do know that every year new and more complex products come out. New fibers, new finishes, films, dyes, plastics, agricultural products, just a few examples. Before making any one of those products commercially, a mass of mechanical problems first had to be faced, appraised, and solved. And here's something important to keep in mind. At DuPont, mechanical problems are solved by mechanical engineers. The company does practically all of its own engineering work, right from the very beginnings of fundamental research. It not only develops process equipment, but actually makes a substantial part of it. DuPont men work continuously on ways to improve existing equipment. They design and build the plants, carry on the maintenance, and of course, supervise manufacturing. Let's consider the opportunities available to you here. Is research and development your special interest? Or machine design? Maybe you're the kind of a fellow who goes more for that. How about plant engineering, including power, maintenance, design, and construction? Or production supervision? Perhaps you lean toward this kind of work with its handling of people. Let's start with research and development. Some of the work is done here at the experimental station. A mechanical engineer in this field develops mechanisms used in making the company's products. His work may result in a massive piece of equipment like this, or in a delicate instrument like this one. There's never been a shortage of problems for research and development engineers. They run into the thousands, actually. They may lead to original equipment to meet new and specific needs, or to improvement of machines already in operation. Let's look at a few examples. These huge compressors are used in making urea from carbon dioxide and ammonia at high temperatures and pressures. Ammonia pumps like this can deliver about 100 tons a day. At these high pressures, machine work, alignment, and assembly are extremely important. Tolerances are severely narrowed as pressures climb. One of the secrets of this type of high-pressure work is the action of the pump plunger in the packing. Specification of the right plunger material is essential. High-pressure design calls for great pains to avoid stress concentration, such as might occur in sharp transitions at corners. Pulsations at high pressures cause rapid fatigue of materials and give rise to many design problems that fall strictly in the mechanical engineer's lap. Now here's a machine used in the plastics industry. It's called an extractor extruder. It melts plastic, takes the solvent from it, and extrudes it in one operation. Well, to adapt it to DuPont plastics, or to scale it up or down, called for studies in power requirements, heat transfer, and fluid flow. In other cases, engineers often design and develop equipment for use by DuPont customers. Here are two young engineers working to improve a machine that simultaneously forms and expands a tube of plastic material. Or a fellow may get into a project that requires work at super pressures. Here's a field that's really challenging, and young too. Behind a steel and concrete barricade, equipment can be tested at pressures far beyond those used in manufacturing today. After strain gauges have been attached to the test piece and the pressure lines connected, a mirror is placed so that an engineer can observe the results of the test through a periscope on the other side of the barricade. There will come a time when pressures far beyond those of today will be used. 20, 30, 40,000 pounds per square inch. These men are getting ready for the time when pressures even higher than this may become part of industrial practice. When a process or product worked up by chemists moves out of the lab, teams of mechanical and chemical engineers take over. For example, here you see molten nylon being solidified on a semi-works casting wheel at an early stage in the development. Many mechanical problems had to be solved before nylon was produced successfully. And naturally, mechanical engineers had a big part in solving them. Just how would you go about melting nylon chips at several hundred degrees Fahrenheit with as little decomposition as possible? Well, mechanical engineers designed and tried quite a few types of melting grids. Some of them didn't work as well as others, but they finally came up with a grid that did the job. And mechanical engineers designed a precision pump that works at pressures better than 1,000 pounds per square inch, but not before they licked the problems of gasketing, sealing, and materials. The hot melted nylon solidifies into filaments as it is pumped through holes in the spinneret that are almost too tiny to see. Naturally, that spinneret isn't a standard item either. It had to be designed. Nylon fibers are sometimes wound on these spools at a rate of 1,000 yards a minute. How would you go about winding yarn at that speed without any deviation in yarn tension? Sound like an interesting problem? The fellows who developed this traversing mechanism certainly found it so. Let's move on to this petroleum laboratory to see another important part of development work, activity devoted to improving existing processes and products. Here, engineers are constantly trying to improve the chemicals DuPont sells to the petroleum industry. The road to any kind of improvement is filled with facts, and these engineers are getting the facts by studying the action of lubricant assistants, grease stabilizers, and other petroleum additives. Here, engineers are studying exhaust condensates that indicate the effects of tetraethyl lead. Engineers study these things in the laboratory. They study them out on the road, too, in passenger cars, in trucks, through tests under various kinds of rigid control situations. The instruments in this test car indicate and graphically record information on such factors as horsepower, fuel consumption, speed, spark setting. That's the way mechanical engineers, working with chemists, arrive at conclusions which result in better and better engine performances. We have seen that research and development includes developing new process equipment and improving existing processes. It also includes design. The engineering department handles design work for most major projects. In some cases, it is machine design. In others, process equipment design. But always, it is the work of teams of engineers, mechanical, chemical, electrical, civil, and so on. Normally, these are men who make their careers in engineering. They work with engineers from the manufacturing departments to design plant equipment and machines. For an example of major design, how about this huge hypercompressor? It builds gas pressures from 450 pounds to 12,000 pounds in 3 stages. When these compressors were built, you just couldn't buy equipment like it. So DuPont engineers pitched in and designed their own. Or maybe you'd like to roll up your shirt sleeves on one like this. Adapt standard equipment, such as this flue gas generator and its control mechanism, to DuPont's ever-changing needs. Over the years, more than one mechanical engineer has thought hard on this one. There she goes. These are just a few of the problems mechanical engineers work with at DuPont. They are typical of the work in research and development. Multiply them by 100. No, better make that 1,000. And you begin to get an idea of how important mechanical engineering is in this chemical company. Another important phase of mechanical engineering is plant design, layout, and construction. Most companies use outside architects and contractors for this work, but DuPont does all its own. Often the engineers who supervise the construction of the plants also stay on to help get them going. Of course, the design of services to go along with the buildings and machinery is included in their activities. For instance, this nylon manufacturing plant. These ducts are part of an air conditioning system DuPont mechanical engineers help design. During the manufacturing process, air is required at 5 separate temperatures and humidities. That's right, 5. That sort of a problem interest you? As you can imagine from the size of this compressor, air conditioning is a pretty important item in many of DuPont's 70-odd plants. Or say you were tackling this problem, scrubbing carbon dioxide out of a gas mixture. These towering scrubbers work at about 400 pounds. The pressure at the scrubbers forces the solution up the side of a mountain. Here in this tower, the pressure is released and the carbon dioxide passes off to the air. The natural fall of the water gives 200 pounds of head, but doesn't have to be supplied when the water is recycled. That's both equipment and plant design in a big way. Speaking of design, how about control instruments? That sort of work interest you? They are very important in plant design, and the advances in this field have been tremendous. Matter of fact, control instruments today are practically a must for nearly every phase of manufacturing operation, because they've come to mean so much in terms of safety and economy. Take a look at this maze of pipes, for example. To get maximum production yields, reacting chemicals must be brought together under conditions as nearly ideal as possible. All steps in the process must be smoothly coordinated. Actually, some processes of today couldn't operate with instruments of 10 years ago. It's a fast-moving, intensely interesting field. If this kind of work appeals to you, whether you tackle it from the plant design end or from the development end, instrumentation offers tremendous opportunities. Still another field for mechanical engineers at DuPont is plant engineering. This is a fairly broad field, including maintenance and power. It also includes design and construction on sub-major projects that may involve process improvement or plant expansion. Nearly all chemical manufacturing operations must run in mechanical equipment: tanks, kettles, presses, pumps, valves. And this equipment gets heavy use, much of it on a 7-days-a-week basis. It's bound to wear out, and that means maintenance. Part of maintenance is keeping equipment in top mechanical shape, catching trouble before it catches you. Supervising this work calls for real ingenuity, and it involves real engineering ability. Then there's the maintenance of pumps, gearboxes, automatic lubricators, and a great variety of complex equipment and process machinery. Here again is a supervisory job for alert engineers. Helping with the maintenance work are the machine shops at many DuPont plants. The needs of some of these shops are always changing. That means an almost continuous program of mechanical study ranging from layout and scheduling to working up shop standards. Now, let's say your major interest is power. Power is as essential in a chemical plant as it is in any other kind. And the power problems that arise from some of DuPont's complex operations are about as challenging as can be found anywhere. Power engineers at DuPont must supply steam, electricity, water, air, refrigeration, and other services under a variety of conditions. Look at this steam reducing station. It is one of several operating at various pressure differentials. They supply steam at the right pressures and temperatures over a wide range of capacities, from 1,000 to 20,000 pounds per hour in short periods of time. Boiler feed water pumps, compression distilling units, fuel pumps. Almost all power plant equipment needs plenty of engineering know-how to avoid interruption in these essential services. Production supervision is another major activity at DuPont for engineers who like to work with people but still want to put their technical training to good use. The duties are broad and cover all phases of plant operation. Such a job might well include setting up efficient maintenance schedules for equipment, keeping production rolling, maintaining quality, reducing waste, and at the same time, building employee morale. Quality production is determined by individual workers. Each must understand the importance of his job, and it's up to the production supervisors to develop this understanding. The mechanical engineers and others who advance in this work train both wage roll and professional employees in manufacturing processes and the use of equipment, an important responsibility. They also work with development engineers in plant technical sections and the central engineering department. Here their knowledge of the manufacturing process is used in working out designs for process improvement or new plants. In all cases, the planning and conduct of a continuing program of training in safe working practices is an important part of supervisory work. Raw material scheduling, quality standards of intermediates and finished products, handling employee suggestions, all are part of the work in production supervision. The Mechanical Development Laboratory is evidence, too, of how important mechanical engineering is at DuPont. A principal activity of the laboratory is to develop and build full-scale automatic machines to be used as models for those in manufacture. The Wilmington shops are still further evidence. They make special equipment and machines for company use. They are among the most completely equipped in the country, and it's all top-notch equipment, ranging from small bench lathes to large diameter boring machines. Notice that this radial drill press has built-in pits for deep drilling. And how often do you see a 50-inch magnetic chuck? Makes possible the grinding of filter press plates and frames. Here's something else, a 12-foot vernier gauge that, in spite of its size, is as accurate as the best of the smaller ones. This optical comparator shows up errors on machining as small as 2/10,000ths of an inch. And here's a micro drill that puts holes in hard metal so small that you have to use a microscope to get a good look at the hole it drills. Yes, a mechanical engineer has quite a bit of elbow room around here with all this equipment to serve him. Now that you have an idea of what does go on in a chemical company, you can see that instead of no opportunities, a mechanical engineer has many opportunities to use his abilities and training, and in many fields. Because DuPont's 10 manufacturing departments operate to a large extent as 10 separate companies, the way a man heads towards his goal varies from department to department. You might start off working with a man who has had many years of practical experience. You collect material, assemble data, make calculations. In other words, learn the ropes. Gradually, you'd take on more and more responsibility until you've had enough experience to size up a problem, develop a method of attack, lay out a schedule, determine costs, and see the project through. In short, be on your own. In the manufacturing end, DuPont has several types of training programs. You may begin on an informal basis in a plant, as with some departments, or you may attend a formal training program that includes conferences on leadership, procedures, employee relations, company policy, and safety. In either case, you have every opportunity to get a broad picture of the company, as well as to learn your job. But regardless of which way you go, you'll find vast sources of information for your use. Fine libraries with technical, trade, and patent literature. Over 100 engineering consultants within the company, each an expert with years of experience, metallurgy, stress analysis, power, lubrication, instrumentation, yes, even meteorology. At DuPont, there is a never-ending need for better machines, better ways to do new things to meet the challenges of the future. Research and development, design and construction, production supervision, and all phases of plant engineering unite to meet these challenges. Mechanical engineers work with each other and with specialists of many other fields towards a single objective: better living for mankind through new ideas, new methods, new products, and improvements on existing ones. There are many opportunities to contribute to this objective, and while doing so, there is the opportunity to express your creative talent and ability, to accept real responsibility, whatever your field of training. Yes, in such an environment, you can look to a bright future with confidence and optimism.